Today. So our presentation, so I can stop talking. We have Robert Ryan. He's the principal of Earth Cycle Technologies. He's a passive house certifier and passive house design consultant. He is currently working actively on certification of projects globally. I know he certifies a number of projects in Canada. He's an approved thermal modeler and calculated thermal bridges for over 10 years for a wide variety of construction types. So I am going to stop my, stop share, and I'm going to hand this over to Robert, and he can start his screen share.
Okay, so can you see my, yep, okay, great, good to go. Okay, so I suppose for me, given this webinar now in the hope that people can make their way to the course, is to fill what I think is a gap in certification. A lot of people struggle with thermal bridge calculations, and I just hope that this is really of use to you guys. Some of the stuff that we're going to go through today is what a thermal bridge is, okay? So I remember when I first went to my first thermal bridge training course, coming out of the course, I actually was, I was boggled. I was completely disorientated. It was hard going, and the one thing that I took out of it was that all you are doing in a thermal bridge calculation is correcting the curved heat flow at a junction in the building. And I'm literally going to explain it to you that simple. That's all it is. We're just making corrections for each of the different places where you've got inhomogeneous heat flow. I'm going to talk a little bit about the principles of thermal bridging in this presentation, and things to watch for, things that are going to cause you problems, and the simple principles of how to organize your construction so that you don't get a thermal bridge problem. So even without calculating it, this presentation would be useful for an understanding as well. I'm going to go through some common mistakes that I see come up time and time again, both in passive house construction and in high performance. The effects of the thermal bridging on the energy balance. So what I've actually done for this presentation is I've modeled a reasonably small building, a hotel, and something similar to a nursing home. And I've taken a couple of key junctions and shown what effect those key junctions have on certain building types. So it gives you a feel for, okay, what does all this thermal bridging, what kind of impact it has. Moisture movement in construction, don't worry, we're not going to go into WUFI today. And unfortunately, we won't be going into WUFI in the course as well. And for anyone that doesn't know what WUFI is a hydrothermal moisture movement simulation program. And I just want to clarify, I am going to talk about moisture movement, but that is almost a whole science in addition to thermal bridging. And it although we talk about it here and on the course, it's almost a separate science. So just to manage expectations. Rules for thermal bridging and standards, I think I'll touch on that. And what we'd like to do in the second half of the session is actually take you through the thermal bridging software that we're going to use for the course. And we're basically going to calculate a thermal bridge live here on the fly. We'll just try and do something simple. We'll also have a question and answer session probably before we do the demo simulation and then after the demo simulation. Okay, so straight off the bat, what is a thermal bridge? This is a timber frame wall section. And maybe if you can just confirm in the text box, Chris, if you can see my cursor.
Yeah, we can see Bob.
Right here.
Great. Super. Thanks, Louise. I just had to make sure of that. So here what we have is just an intermediate floor in a timber frame wall with a brick outer leaf. And as you can see here, there's a little curve going on here. But as you go to the ends of the sections, the heat is moving homogeneously. It's just running straight out along the length of the section. And what we're doing in thermal bridge is we're taking the losses for this piece of construction and taking away what PHPP would have assumed. Because in a PHPP model, it just takes linear heat flow across the area of the surface or the length of the junction and applies it everywhere. It can't do this curved heat flow here. And all we're doing, if we take away the section with the curved heat flow, if we take the section with the curved heat flow and take away the homogeneous section, we're left with psi. Okay? And that's all we're doing. It does get a lot more complex in terms of what buttons you have to press and what you have to do. But in reality, this is all it is. And you can get into all the complex equations you want, like the L2D and all the numbers and all the rest of it. This is all we're doing. We're just correcting the heat flow to make a more accurate energy model. Now, there's a lot more to this than just correcting the heat flow. We're also looking at if we're going to have surface damp or mold, if we're going to have surface comfort. And there's a lot of other tricks that we're going to see as we move further on through the presentation. Now, that's for, you know, a straight section, that intermediate floor. What happens when you come to a corner like this? This is, I think it's the same timber frame construction. It might be a little bit different. But basically, this is an external corner. This is inside, this is outside. And what PHPP does in its measurement alone is it creates, again, straight sections like we've seen in the previous example. But as you can see here, it overlaps the heat flow accounts at the corner. Okay, so you probably wonder to yourself why you see in Passive House, if you've done the Passive House training, that there's a negative value. And that basically means that the corner is not as bad as this overlap that occurred at the corner. Okay, and that's how PHPP estimates some amount of heat flow for the corners in the building, because the reality is that there's always additional heat flow at a corner. And, you know, plainly due to the fact that it's just a corner and that it has more surface area on the outside than on the inside. So heat's able to spread out from that corner to a bigger surface area on the outside, thus giving more heat flow. But because PHPP overlaps the dimensions, it has some allowance for that. And if you get a minus psi value in PHPP, now you know what that's doing. Now, let's get on to the easier parts. So, aligning all the thermal elements in your building is the most important part of high performance or passive house. The thermal elements that we have are obviously the insulation layer, windows, the thermal break in windows, glazing units, the thermal break again and how that connects with insulation, and then thermal breaks and products that we use to bridge one insulation layer to another. So we've basically got insulation. Glazing is obviously a thermal layer. We've got triple glazing and quadruple glazing in some of our projects. Steel and aluminium are the big no-nos. Okay, so as you'll see as the presentation goes by, steel and aluminium are highly conductive. Stainless steel is not too bad, but it's still highly conductive. Concrete is highly conductive. All these elements need to be broken by thermal breaks. And what a thermal break is basically a structural product like PVC, aluminum, or sorry, PVC, compact foam, aerated concrete, cellular glass, any of those, they're all our thermal breaks. And I'll have loads of examples of these quite soon. Now, the all-important aspect is having a complete line of continuity, both in section and plan, where you use thermal breaks everywhere to have a solid connect all the way around your envelope. If there are any leaks, you will destroy the thermal constant of the building. And I have had so many experiences where I visited projects and, you know, there was a thermal bridge discovered that where it wasn't implemented correctly, and we've mitigated the thermal bridges, and all of a sudden the house stabilizes and holds its heat for much longer. So it's vital that we get this right at the start. Excuse me for one sec. It's vital that we get this right from the get-go, because obviously retrofitting thermal bridges is not an easy thing to do. Now, I see a mistake here. A great side, oh no, I haven't, sorry. I'm doubting myself. So in terms of psi values for passive house, a great psi value would be anywhere from between minus 0.04 to minus 0.02. Generally for a corner, that's normally the case, okay? A good psi value is anywhere up from there up to 0.01. And these are all metric values. You can use the video in the presentation and some converters in the PHP if you need to get the IP, but all of this presented in metric. Then a moderate psi value is anywhere from between 0.01 and 0.08. A significant psi value you can see, and you know, we can read on and on as we go. Any of these significant or poor psi values, the thing you have to start watching when you get something between 0.08 and 0.17 is then you have to start looking at comfort, because it might be such a bad thermal bridge that comfort is inhibited, or even condensation at the worst case. Okay, so just nice to have a range of psi values there and that indicate what kind of values are good and which are not so good. Now, common problems found, actually this would be the kind of thing that you would find in Ireland quite a lot at the moment. There's only 12 approved thermal modelers in Ireland, and there's a population of, I don't know, 6 million or something like that. So you can imagine that with 12 thermal modelers, it's hard to get around everyone. But basically, a stagger in the insulation layer where there's no connect could cause you a psi value all the way up to 0.12. And you can see that there's a tiny connect there, but still shocking psi value. You would reduce it nearly by, well, you'd reduce it nearly down to nothing if you simply continued the insulation over it. Okay, so that's the importance of connecting thermal layers. Thermal breaks, things like shock and Farad and all that kind of thing. Fabrica, there's loads of them. But basically, if you had a connection, and what we have here, these are just RC examples. They're very basic examples, but they follow suit for what we want to demonstrate. If you didn't line it up, and I've found this in so many projects, that you know, people put in a thermal break maybe between two steels, but they don't sit it right in the plane of the insulation. And you can see the difference here. It's 3.5 times more for not actually aligning that thermal break with the insulation. And like thermal breaks, especially in this case with a balcony connection, you know, it's very hard to get good values or thick thermal breaks and still be structurally viable. So, you know, if you're going to go through all that trouble, expense, cost, and, you know, the thermal break is only as good as it can be, not putting it then in the insulation layer, you might think this sounds stupid, but it has happened so many times. Here's a massive one in Ireland, and I think in every corner of the world, putting windows on top of the structural layer rather than out in the insulation layer. This is a big no-no. And I think all of us can identify in bathrooms with the black rings around the window, because the surface temperature is so cold, even in insulated houses. And basically, you can see here, you could get values of up to 0.2, whereas if you put it in the insulation layer, you can be all the way down to 0, depending on what thermal break you use to support the window, or whether it's wood or whatever it is. These diagrammatic examples are just to show you the impact of generic situations. Here's another one that you know, is not so obvious. You often see parapets and steel frame, or see construction, and, you know, timber frame is not too bad, but definitely in the other two, wrapping long extended pieces is actually not that effective. I recently had a project in a place called Kilkenny in Ireland. It's a big tourist attraction, and it was a landmark building that really wanted to look well on the corner of a bridge with a river and all that kind of thing, and it was really beautiful. And they wrapped entirely huge balconies and parapets and all that kind of thing. And we then ran the PHPP, and I stepped in to do the calculations, and the results were absolutely horrendous. And by adding a thermal break and wrapping it, we got some decent values, but wrapping it alone doesn't always work. And the beauty of having this skill and this program is that you can test these alternatives rather than making qualitative assumptions and seeing problems later on. Here's another one. It actually stated in our regulations at one stage that thin metal layers could be omitted from the calculations. That is now not true and not the case, because as you can see here, with aluminium, okay, so just one strand of aluminium at 1 millimeter thickness, going through the insulation layer will cause 1 millimeter will cause a psi of 0.1, 2.123, and you can read on there. But as you can see, these are huge psi values. This is in our significant range of psi values, and they're really, really quite high. And where this is most common is aluminium starter tracks. Nowadays, what we do is either use a PVC starter track, or we just use a drip edge on the outside and a starter piece on the inside, and then use a rubberoid flashing over it, you know. But it is something to watch for, and can cause massive heat loss in buildings, in passive house, and can be overlooked too. Here's a big one, and I'm going to show you an example of this now in a minute, but shelf angles. There are ways to get over it, but in very tall buildings, the shelf angle is one of the longest lengths and one of the most prominent thermal bridge. So we'll look at that now in a minute with some examples. Now, some of your helping friends, I know that in the US you have General Plastics and Armatherm that do thermal breaks. You do have cellular glass. Aerated concrete I have used in some US and Canadian projects, but it's not that common. Wood is actually a thermal break. You know, when you're doing timber frame construction, you can get down to super levels of insulation. And depending on how you use wood, it's quite advantageous when it comes to thermal bridging, and you can get a lot of negative psi values and get a benefit from that in your energy balance as well. PVC and nylon and armadillo fabrica are all great for high load thermal breaking. Wood fiber, this is more an Irish thing. It's actually a Central European thing. We got it from Germany, but it's sold here. But you can get some really high density like Bosig and Phonotherm, which is like a wood particle board that serves as a thermal break. And you know, some of those products can take a higher load than we would conventionally see in. Rigid recycled plastic, compact foam you guys have over there, and I don't know if you have this, but Alma Tea, that's another one. It's basically all our old plastic bottles melted into an insulation product that's similar to wood, and you can cut it with a saw. All these things are super, and like compact foam we're using underneath windows, anchored to concrete structures, anchored to steel structures to hold serious weights. And you know, it has such a low conductivity. It's in the range of 0.049, really super stuff. And then glass reinforced plastic in some forms can be used as a thermal break, especially in windows and things like that as well. So that's just some of the products that I know of that I just thought I'd throw in to explain, look, there are things there to help you with your detail and your design solutions. Now, steel penetrations. Generally, if you're going to penetrate your insulation there, you're better to penetrate from the inside towards the outside, okay? And the reason being is that it'll draw the heat into the steel and out into your structure or your insulation layer and warm everything up. The case when you have steel going from outside towards inside is a lot more damaging, because you're dragging your heat out of your building, causing cold and potentially moisture problems. So I just wanted to touch on that before I go ahead with this slide. This is just explaining generically that, look, the more you penetrate with steel, obviously the higher the psi value, but look at the difference. You know, 45 times greater heat loss if you have steel going from inside to outside. So I cannot stress that steel is fine in construction if it's broken, if it has, you know, reduced cross section, if it's done in a certain way, but just take care with steel. So again, on the same principle of the steel, here we have just our structural layer and our insulation layer. And basically, if our insulation is on the outside, we have a warm structure and very little problems with moisture. If we have our insulation on the inside, then we're going to get structural damage on the outer wall and possibly condensation as well. And this is the most important aspect of passive house and high performance building, is to always keep your steel structure or your timber frame structure or your concrete structure inside so that it's kept warm, and then wrap everything on the outside. Now, there are exceptions, but they have to be dealt with in almost every case with a hygrothermal simulation, where you can track the moisture movement in the wall, because there's so many factors. Like one thing, hygrothermal takes into account climate, the amount of materials absorbed, rainwater. There's so many things involved that it has to be taught as a science in itself. But generally, if you're externally insulating, you're on the safe side. Now, I feel I'm speaking a little bit fast. Is everyone keeping up, or how's the mood?
So far, so good here. Well, all good.
Yeah, you're doing okay? Okay, I'll try and slow down though because I'm a good way through. Okay, so what I've done here is I've just got some examples of, again, they're just generic examples. I mean, we couldn't take real details or anything like that. But basically what we have is this is actually reinforced concrete with external insulation. And what they've done is just flanked the insulation both inside and outside of the parapet. And this is something I see a terrible lot, like, you know, and the psi value that I got from this model was 0.4. Then if I covered the top in insulation, I got it down to 0.3. And then if I broke it, I got it down to 0.2. Now, if I had it covered the top and broke it and maybe used a better thermal break like that cellular glass or a couple of rows of aerated concrete, I'd have maybe got this down to something more like a passive house psi value. But nevertheless, I took that value and I applied it to a small building. Now it says a house, but we've got a treated floor area here of 377 square meters. That'd be more like the house I'd want if I won the Euro Millions. But as you can see here, if we just apply this thermal bridge to the parapet of a building this size, the additional effect of that thermal bridge on the energy balance in PHPP will be plus 5 kilowatt hours. Okay, now the target in PHPP in passive house is 15. That's 1/3 of the allowable allowance. And even with my upgrades, the lowest I could actually get it down to was 2.56 with this detail. And again, I'd really have to optimize that detail in order to get it to work in this instance, because trying to compensate even for 2.56 kilowatt hours, that will be hard with a building of 377 meters squared. So next I applied it to a hotel. And what's happened here? It's only 0.5 kilowatt hours in the worst case, 0.384 in the intermediate, and 0.24 in the best case. So you can see that if you have a huge hotel or a very large residential building or just a very large building, you can absorb thermal bridges that bit easier. But as you'll see now in a minute, what you have to watch for is the magnitude of the thermal bridge. Okay, so in an example now in a minute, I'm going to show something where it's a similar detail, but it actually blows it out of the park. Okay. So again, I applied the same detail with the original and best case to like a nursing home kind of, well, just maybe some different shapes, size residential building or multifamily. And you can see it wasn't as bad as the small building, but it's still pretty bad. It's probably just about tolerable. So next we have an example intermediate floor where there's a continuous steel. This detail came from a detail I was working on the other day, and it's kind of like a shelf angle, but it's actually just bracing the structure to what's a very large wide of brick. But nevertheless, I thought it'd be useful. Nevertheless, I thought it'd be useful because it's continuous steel and it's similar to a shelf angle. Now, if we had continuous steel, the value that we get for the thermal bridge would be 0.47. A break behind does a little bit, but not an amazing amount when it's continuous steel. And a point connection, as you can see here, where they just have broken squares about a 1 meter center, would get us down to around 0.08 to 0.15. So let's see what effect that has on our little building. So the original was plus 6 kilowatt hours. The point connection was plus 2. Okay. This is the big one, okay? So when you have a very tall building, you've just got intermediate floor after floor after floor after floor. Now, even given that, when I applied it to the PHPP, still wasn't as bad as I was going to expect, but nevertheless, it was almost 10 kilowatt hours of the 15 kilowatt hours allowable. Still crucial, and with the optimized down to plus 3 kilowatt hours. Now, just imagine if you had intermediate walls that broke your insulation layer. It's a very similar effect. And this is why I'm saying you have to constantly focus not just on the psi value, but on the magnitude of the psi value and how long a length it's going to occur for, what the size of your building is. And having tools like Design Passive House, the SketchUp plugin and PHPP, and this mold simulator and the thermal bridging course that we're doing enable you to not guess it, but get it right every single time and not have to rely on someone like me who does the thermal bridging consultancy. Okay, so here's an actual detail where the architect actually said, now he allowed me to use this as long as I didn't mention him. The architect thought he had a super detail here, and what he had done was, it was a masonry or a concrete structure with insulation in a cavity and a brick or a masonry outer leaf. And he had internally insulated the window. He had covered the face of the window in insulation, but the window was aluminium, and the thermal break in the window is actually this piece here and this piece here. So this detail came out at 0.374. Generally, for a passive house window fitting detail, you could be as low as 0 or 0.01 or 0.04. And the reason that this detail actually ended up so bad, even though we'd spent all this on insulation and labor, was because when you try and overlap an aluminium frame, it's basically pointless. It will drag the heat through the aluminium out of the construction. And the solution in this case was to use the same window, the same materials, and just reorganize them in a different way so that the thermal break aligned with the insulation. And that's the crucial element of detailing to passive house, is to align all the thermal breaks so that they're not, and we actually got 0.04 on this. Now, here we have, okay, so in one case, the building wasn't actually making the standard anyway, okay? So this should be 15 if it's making the standard, but it's just the way I had the model set up. But with the bad detail, it'd shoot all the way to 25, nearly 10 kilowatt hours more. And with the good detail, it was down to what should be making the standard if we just change the U values. In the large hotel, the bad detail took the building from 12.6 kilowatt hours per meter squared per year, right down to 4.2. And in the nursing home type building, 23 down to 15. So you can see how the effect of, if we applied this detail to all the windows in the building, you can see the massive dramatic effect that windows have on the energy balance. And windows are one of the longest lengths of thermal bridge in any building. Thresholds, although of small magnitude normally, are an important detail in terms of condensation. This one was pretty bad. It was 1 watt per meter Kelvin. So it's, you know, it's right out of order. And it was basically held up by steel. They had a thermal break. They insulated everywhere, but they didn't insulate this piece. And it was super bad, super bad. And the same cost to implement it correctly. Then the updated model was to just build everything up with thermal breaks, make sure that the thermal break in the door threshold aligned with it. And there we have, I think this may be wrong. Maybe it is though, 0.15. But as you can see in our previous slide, the surface temperature, even though it was a decent window, was 13.25. We got the surface temperature to 15.78 degrees. Now, if you have a high psi value here, and really we should have 16.5 for comfort, but if you have a high psi value here and you've achieved a surface temperature, for a threshold, if it's just one small front door, it's not going to be the worst thing. Here we have another threshold. This was a detail given to me by an architect that said I could use it. And okay, so in this case, they had some kind of terrace thing sitting on grade. They had RC coming down, RC and RC ground floor, and it was externally insulated on the outside. They tried to put in some perimeter insulation here. They actually had a steel angle holding up the threshold, and had packed in insulation, and actually had a thermal break here that was doing absolutely nothing. So as you can see, a lot of people make mistakes in construction because they don't have this tool of being able to calculate thermal bridges. And what ends up happening is they go through massive cost and not actually getting any benefit. Now, we went through iterations to try and retrofit this, and we found that we needed to get to 15 degrees, which is an FRSI of 0.75. And eventually we got there, but it took quite an amount to even just get it to 15 degrees. So if I just skip back here, sorry, that was a bit bitsy. So the first amendment was to add an AAC block. The psi value was still 1 or thereabouts, and the FRSI still wasn't above 0.75. Then we increased the insulation by 0.5 meter, and we got it up to 15.18. And then we did another 0.5 meter, and we got it up to 15.32. But the psi value here was still 0.9, like it was abysmal. This wasn't actually a passive house project. It was a high performance building, and the project, they conducted the study, and I don't know what they did with it afterwards. Now, remember what we said about PHPP only being able to create U values for homogeneous sections? I think anyone that's working in PHPP would know that it can do an estimation for timber, which is grand, into ISO 6946. But when it comes to steel, if anyone's experienced with passive house, they'll notice that when you calculate U value for an assembly in PHP and you put steel in it, it'll say error over 10%, finite element calculation needed. And through using our program, you can calculate sections with steel and calculate a user-determined OR value that you can then put in PHP. So that's one of the great things that comes out of the mold simulator software. It's not just psi values and chi values and FRSI. It'll actually do your U values too. Moving on from that, it'll actually calculate, as you should, with cladding attachments. Apologies, I keep pointing at the screen, but I need to use the cursor, apologies. So you can actually calculate full 3D models of cladding attachments with their bolts, with steel studs, and it'll actually calculate an OR value based on a 3D assembly if you want that. Moving on even further, you can calculate, now I borrowed this slide for the moment from a previous presentation, so this is not actually the mold outputs, but they're very, very similar. So you can do steel point connections in steel assemblies with, you know, umpteen complexity. And one I was just working on earlier today is a psi and chi. And actually we could add an added bit of complexity to this and put in a third plane. But you can calculate something like this. These images were rendered in SketchUp where I built the model for the mold. This is one of the great things about mold. Our examples show how to do three-dimensional modeling for SketchUp for import into the software. You can also draw in the program, and you can also draw in Blender, IFC, Object, Collada. There is a range of different formats that it will accept, and Blender actually is another one of free software, and it will actually import them into it, and then you can do all your presentation in SketchUp, or you can do, there's tons of presentation in Mold as well. And look, we're just coming up to what will be a natural break for some questions, and we're in good time as well. So what we're going to do in the next session is I'll be able to show you all of this. We're going to run through a very simple thermal bridge, and I'll give you an oversight through the program and how it works, and you can actually see it live on the fly. I tried to calculate that detail that I just drew earlier, but I didn't have enough time, and there's a couple of errors in it. Any experienced thermal modeler would know what they are, but all of this is possible with the software, and it's demonstrated on the course. Maybe I should actually take in one of the course examples. Louise, should we take we should really do some questions and answers and then take a short break. What do you think?
Yeah, Louise can answer that.
No, Chris, you can go ahead though.
I was going to say, if there is, I think we've been staying up with the chat quite well. Does anyone at this point have any specific questions? I think Louise just pointed out, I think it's clear there is a piece of software. Marcel alluded to it. It's called Mold Simulator. Louise has posted the link in the chat.
Yep.
That is a big part of the component where the calculations are being made. And I believe in this presentation, Robert's going to go a little bit deeper into that specific software for the second half. But is there any questions at this point for anybody? I would raise hand, text, unmute.
No, the only question popped up, Marcel actually answered. It was a question from Simon asking, how can we know the psi value? Is it by testing or calculation? Marcel got that one, but Bob, if you wanna actually answer that one as well, just to make sure that everybody gets the answer.
Yeah, definitely. So all of those psi values that were in the presentation, I actually calculated in the mold simulator package. And that's what the whole course is aimed around, is showing you how to use that package to actually calculate those psi values based on any kind of construction.
Yeah, and another note here, once you're actually talking about thermal break section, during the thermal break section, Marcel actually alluded here that he's been using the aerogel successfully behind the brick shelf. It was just
Oh, okay. That's good. And you can model that in this as well. Maybe we'll model that one, ask him. No, it's a bit too complex, actually. I'll try and keep it simple.
I think let's do a quick, unless there's any other questions at this point, maybe a quick minute or two break, and then we'll get back at it. We're 11:58 on my clock, so maybe 12 o'clock, just a small break. And if any questions come up, just poke your hand up.
Yep. Take 2 minutes break though.
2 minutes, yeah.
All right. Yeah, so it's a 2 minute break though. Just to let you guys know that the course that Passive House Canada is going to be providing, it's actually developed by Robert Ryan, your instructor for today. And it teaches you how to calculate thermal bridges using the mold simulator. I put a couple of information in the chat box. Passive House Canada students will have a nice discount. And Bob can definitely speak about a little bit more about the software during the second half of the presentation, though. So if you have any questions about anything about the course, the software, just let us know, and we'll be happy to help.
Jason, are you there? Do you want to mute and ask that question, or I can muddle my way through it? It's in the chat. Is the boundary condition being set to RSI 0.25 surface film on the interior for the FRSI checks?
Exactly, yeah. And it's with boundary conditions of 20 and not. And your FRSI that you need to meet is 0.75. But you have to use a formula to figure out what the surface temperature is at a different given climate. Okay, so I typically use the one set of boundary conditions all the time for FRSI and for thermal bridging, and typically I just use that one set, calculate the thermal bridge, and then I have my own calculator which I'll share with you guys that converts the temperature for a different climate. The climate temperature that you should use for FRSI is the colder of the two weather condition temperatures in the heat load sheet. So you use that temperature in my calculator to find out what it is for your climate.
I would say, hopefully, that Jason, that answered your question. I know that you mentioned to me privately, so I just posted it to everyone. I think that's probably our 2 minute break, so I would get back at it, Bob.
Great, okay. Now, hold on. So here is Mold Simulator. And starting out, you've got a series of tabs here. The first one is just setting up what the heat flow direction is and the gravity direction. So gravity is obviously down if you're looking straight forward. Gravity is into the screen if you're looking through a planned section. And then the heat flow direction, this is not that important, so I'll come back over that later. Then you've got your flanking elements. I'll talk about that in a minute, but that's basically setting up the parameters of what U value goes where. And it'll make more sense when we run a simulation. Then you've got materials, and you've got a material library in there with like stuff that you can add to. You've got a generic library as well. And you know, you can save out these, pop new ones in, make libraries, save them in folders, import them, all that kind of thing. It's great, super great. Then we have this 3D building section, which we haven't touched on, and mainly because it's just so much easier to draw it in SketchUp and import it than it was to use this thing. So we're kind of abandoning the middle one. Then we've got boundary conditions, and I have a standard set of boundary conditions that I send out with the course. And these I'll explain again in a minute when we get to it, but they're just setting up the temperatures and the surface film resistances on the inside. That's a little bit of advanced. Now, just bear in mind that when you sit the course, this will all be explained much, much, much slower. And it'll go into great detail on it as well. But the reason I'm just giving a synopsis is because we're going to just roughly see what it takes to actually perform a simulation. And then the last tab is just the simulation tab with all its settings. Okay, so I'm going to start by actually drawing in the program. It's very similar to term LBNL, only it's a little bit more advanced. And I think I'll just draw a corner of something. Let's do a timber frame section. So it's got, like CAD, you just press line, click a point, and then if you hold shift on the keyboard, you can snap to 45-degree increments. And then if you press enter on the keyboard, you can type in a distance. So let's make this 1.5 meters. Let's do a simple wall corner. You can also offset a line. So if you grab the points that a line makes up, you can offset it. Press enter. X, Y, X minus 150 because we're going this way. And it'll offset it. Actually, that just moved it, but now and ever. You also have rectangle. And if you're drawing a rectangle, again, if you press enter on the keyboard, you can enter in its dimensions. So height 150, length 1800. Okay. Now, I'm going to put a little rectangle in here. That is 44 planed. You can also move points in here. Y minus 88. Don't worry, this is explained much slower as well in reality in the course. But I want to give you a synopsis. I want to give you a taster. Anyone that's calculated thermal bridges before knew how painful this used to be in other software. Now it is so simple that my 5-year-old daughter, I'm sure, will revel in it at some stage. Right, let's put a load of timber in the corner just to see what it'll do. Let's put another one here. Okay, that'll do. Now we'll put on some gypsum. And if it gives you any confidence, I know I've been doing thermal bridging for a long time, but I've only had this program a number of months now. And you can see you get used to it quite quickly. Now, what you could have done here was just brought in a CAD detail, and it will be the very same thing. In fact, I'll show you. Hold on, let's save this. Won't let me. Oh, it's because I'm drawing. Save as. Example. And then file. So if I was going to just take in a standard CAD file, and I have a CAD file here. So there's the wall assembly that we were doing earlier. And if I want to bring that into mold, all I have to do is go file. Actually, I'm going to open a new one. File, import, DXF. It's a DXF that it takes in, and a standard SketchUp DXF is fine. I haven't tested all programs, but most of them. Oop, wrong scale. It's in meters. And you can import in inches. And the program actually works on IP units as well, although I haven't ventured back into IP for the training yet. Okay, so that brings it in. All the little bits perfect, just as they were in the CAD drawing. Excellent. What you can also do is, when you're finished your calculation, if you made loads of changes as you were going, which we're going to do now in a minute, it will export whatever all the changes were as a CAD file. So you've got it going in and going out. It's the first time I've ever had a Thermal Bridge software, and I've spent thousands and thousands of dollars on Thermal Bridge and software trying to find something like this. And I'm surprised I didn't find this at the start. But it's always the last place you look. Now, so that's all our materials. You're probably going to ask why I didn't model the repeat and studs going out. The new conventions are that you only model the ones in the corner. And if this is a full repeat and you're certain that it is, you don't even have to model this one. And the reason being, I won't get into it now, but just for the advanced thermal bridge guys, I just want to clarify wall 1, or at least highlight what I'm doing. Now, that stretchy thing that I just put in there is called a flanking element. And basically what it's saying is, I'm taking the U value through here over this straight length. So if you remember in the presentation, if we grab our corner, oh, bear with me. So if you remember in our presentation, we had our detail, but then we had this. This is what we're taking away. Sorry, this is what we're taking away. This homogeneous heat flow. Well, this length is the same as the length in the big detail, and the U value is the same as it is at the ends of the sections in the big detail. So what we want to do is, like, really, you can move this down here just to make it visually correct. Take the U value at the end of the section and apply it to the whole thing. That's what PHPP would have assumed. That's what we're taking away. And the difference we're left when we do this for both sides is the influential heat flow at the corner. Okay, so let's do the other one. Oops. That's all I need to do. Now, materials. I'm going to go into my library. My library is very messy, I'll warn you. but nevertheless, it's got some good stuff in there. Let's get wood. Oh, sorry, I've taken it off the screen just out of habit. And you can save these libraries and have a library of libraries and all that kind of thing. Oops. I'm just going to pick some generic materials. And maybe some woolies in here. Now, literally as quick as that, you can throw materials into these things. For anyone who have used term, you know the pain of even getting to this stage. Another cool thing this program has, and which we use in Passive House, is automatic cavity detection. So all you have to do to create an airspace is paint it, and that's it. Just set the direction of the heat flow and paint it. And you've got one for divided airspaces and one for air layers, both of which are explained on the course, and I won't go into too much detail now. Next, we have boundary conditions, and this very like term, only it's even better. So we've got inside horizontal, because this is a plan, and then all you have to do is basically click the boundary condition in the library and then paint it on. For the outside, it's actually sheltered, so we go sheltered horizontal. And now, if you want to paint the adiabatic, which is just like a null set, it's explained on the course as that. It's basically, it's not taking in or out heat flow. I'm just going to undo that, because if you press this button, it just paints the whole thing. Everything that's touching. Beautiful. Are you ready to rock? That is a thermal bridge in 13 minutes. I'd love to be able to see you guys now, because I'm excited and I hope you are too. And here it has the psi value minus 0.00597. It's not much of a report looking at this graphic, but if you go into reports, and if I go into 2D, here's one I made earlier. No. Here's the kind of report that you can get out of it. So it shows you your subdivision mesh, your boundary conditions, your airspace, everything, thermographic image, all the outputs. And this is highly customizable. I never stop actually changing the outputs on and the report and stuff. I'm always at it. Okay, so any questions, guys?
No questions here, Bob, but we said on high, nice. So it seems to be everybody's a bit depressed on how fast was it, though.
Well, I like making life easy. I'll just show you as well, like, you know, let's say you're like, okay, builder, I'm not going to have a stud within one. Actually, no, I wouldn't do that. But let's say you're going to fill in this tiny little block here, or even get rid of this here. You're going to have something like this with maybe insulation in. You can see, now I know I'm rushing through this. I just don't want to bore you. But you can see how you just lash through it. Like, you know, it's quick and easy and dirty, and I love it. Now, it might take a little bit longer to simulate because I have 64 gigs of RAM and 16 cores in this machine. So it's a bit heavy duty. But even on my laptop, it's really quite quick to simulate. Now, 3D takes, if it's a really complex 3D like this one that I was doing, it took on this machine, this one, that took an hour to simulate. And that's kind of round about the time that it maxes out at. Like, you know, it never maxes out, but I've never been sitting waiting longer than an hour. And just to let you know, when I was using its previous counterparts, not this software or anyone that makes it, but just a different software that was supposed to be the most advanced, I had often sat for 3 days. And not only did I have to sit there and wait, I had to wait for it to stop, perform a small calculation to check its accuracy, and then run it again and check its accuracy, and run it again and run it again and run it again. Sometimes there could have been 12 iterations over 3 days to do what I've just done there. So for anyone that's already doing thermal bridging, I think this is just actually insane. Would anyone like to see a 3D thermal bridge done in maybe 15 minutes?
Bob, we have a request here. Can you show the FRSI as well?
Yeah.
Yes, please, 3D as well.
Cool. Okay. So I have to open a different report because it's slightly different calculation, slightly different boundary conditions. Let me just see. Condensation and flows, flanking condensation and flows. Oh, it's broken. No, it's not. There we go. 18.16 and it's 0.908 is the FRSI. You happy enough? Like, in fairness, it's 150 mil stud with 100 mil of polyiso outside it, so it's bound to have a good FRSI.
Oh, it's muted. Perfect.
Excellent.
We have a question here from Elise asking, have you ever worked with Flixo? And if so,
Yeah.
what are your thoughts compared to Mode?
I have used Flisco, Trixo, On-Term, Sci-Term, what else have I used? Term itself, of course. I've used nearly them all. And Flixo is great, absolutely great. But the only downside, and I don't know why they did this, was it was 2D, and that's all. You know, it doesn't do any more, it doesn't do 3D. And then the air cavities, it was very awkward. They've probably done lots of updates since I last had it, but it was a little bit awkward, more awkward than this one. And this one has little bits of awkwardness in its own right. But yeah, no, Flixo is a good program. It's a good program.
Thank you, Bob. Now people are asking for the 3D example, though.
Right. What are we gonna make? I'll just make something random. Hold on, I grab SketchUp. So here's the SketchUp model of that one from earlier as well. Let me see, new. We're not going to calculate that one. We don't have an hour. Okay, actually new from template because I want to do it in metric. Right, I'm not going to teach you how to draw in SketchUp now in the next 10, 20 minutes, but we'll just do something very simple.
If possible, Marcel says simple beam penetration through insulation.
Yeah, that sounds roundabouts where I was heading for. But you know what? Just before I do, watch this. This is cool. Now you're gonna love this. This is. I'll do the steel beam as well, but watch this. Right. So let's say you have a cladding attachment system inside this. Actually, we're gonna do it. We're gonna do it. Sorry. We're gonna do it. So if you have a cladding attachment, and I'm just gonna turn off K for a minute. Let's just put a big lump of steel in here or something like that. Yeah, that'll do. Okay, and let's say it has a really funny shape. 0.01, and it's like 10 mil thick. Found this button the other day. So if I put back in my insulation, unhide all, I'll turn on K for dashed lines. Now watch this. So let's say we want to take that piece out of the insulation layer. We just click that and click the insulation layer and then do it. It's sorted. Look, watch this. It's actually cut it out of it perfectly. So no matter how complex that object was, it will trim it out and have it ready for the software. As long as you have solid groups, you can use solids solids, intersecting solids basically, to take out and put in geometry out of your insulation layer and make sure there's no overlaps. Now the crucial thing in all of this is making sure that your faces, you know, if you draw in SketchUp or any other program, you have to make sure that this front face is out, not like this. Okay, so if you have one back face facing forward, it'll destroy the whole thing. But it has error checking so that you can, find out where that happened. And it also has a weld threshold. So if it's really small and it's to a certain size, it'll actually automatically adjust it. But what I do say is don't play with the weld size. I haven't had much success with it. Now I'm just going to export for our first part a 2D graphic as an AutoCAD DXF. And I'm going to put this in as example 2, 1 straight wall. What I'm going to do with this is ensure that my U value that I use for my 3D is exactly the same as it should be in the 2D flanking element. Now let's turn on this. Then we need to export this 3D model as an OBJ. If you're using SketchUp, example 2 to assembly. Lovely. And then we get to mold. Okay, so we get rid of this one. Have we saved it? Save it. Actually, just before we go any further on this one, if you export this as a DXF, convert it to millimeters or inches or meters or whatever you want. Just type in the scale. And then if I go to CAD, file, open. Oh, that's not it. Where is it? Oh, no wonder. DXF. Export example 1. Voila! So it takes, yeah, this is what we did in the second half. So once you've finished playing around with your detail and molds, you just export a CAD drawing, hatch it up, label it up, all that kind of thing. Beautiful. Now, back to this. We want to start a new one with a 2D wall section. No, straight wall. Where did I put these? Oh yeah, that's it. And that was drawn in meters, I think. Yep. Now, materials. I'm gonna have to pick really simple materials so I don't make a mess of this because we are on the fly. Concrete heavy, that'll do. And extra term CT. And now we'll just do the most simple boundary conditions. Inside, outside normal. Oops. And then adiabatic. Now put a flanking element on it. And this was just to save me actually doing that in PHP. I was too lazy to open Excel. Plus it's more accurate. Lovely jovely. Now, 0.1023, 0.10231. Beautiful. Copy. Now, if we go into the other one and just save it. File, import. Switch down here. Example 2. Now, see here, you have a scale, a weld threshold, which honestly I don't play with, I'm afraid, because it just doesn't work out. If there's something wrong with your model, go back and nearly start it again, because that will actually be quicker. Or identify where the flipped face is or something like that. Most of the time it just fixes the geometry and that's fine. Optimize, yeah, leave everything alone. Yahoo, yeah, boy, yeah. Now, the first thing you have to do when you ever import a 3D model is to click the boundary conditions, because if that happens, you know you've done it right, which is beautiful. So I can actually, you can do it in any order as well, it doesn't really matter. You can start with boundary conditions or start with flanking elements. Inside horizontal, everything. Outside horizontal. My eyes are going blurry. Outside normal is what we picked in the other one. That's it. And then materials. So the only thing that's different. Hold on, what did we do? Concrete heavy. Oops. Isogerm CT. I think if anybody, if call now if this is wrong, but I think it's right. And we need stainless steel. 17. Nice and aluminous. Okay, last thing then in 3D, you have the same flanking elements, only they're area based and not length based, because you're not doing it in a 2D model. Hey, what are you doing? Oh, there we go. So I still have it in the paste menu. Okay, this U value that I'm putting in is the one that we took from the 2D section. Okay, ready, steady, go.
While it's doing that question, can you assign and import materials from SketchUp, or do they need to be assigned in mold after exporting?
You can, and I saw it ages ago, and I thought, sure, look, it'll be grand. But there is a section you can export your materials from SketchUp with the OBJ file, and then in this you can import them into the material and assign them to the material in here so they look the exact same. But I'm a devil. I just use colors. But if anybody wants specific stuff like that, I'm sure we can try and accommodate them somehow. But yeah, it is doable. You probably figure it out. But I generally don't do it. I try and keep the materials in mold as simple colors because of more control over them. I don't know why it is. Probably just force a habit. Well, I'll show you once this calculates. There we go. And our calculation, whoa. Okay, so if we get a calculator, I can't believe that with all the advanced things this program does so well, sometimes you have to do this. Like one minus the other, minus. And what we're doing is, taking the 3D heat flow and subtracting the flanking elements. Come on, which is the sum of u values by areas. Oh, it's 0.408. I can do that. There's our chi value, 0.07826. Is anyone excited?
Yes, here. Yep, that's great.
Yay! Well, just bear in mind that it's explained in so much more depth in the course. But I knew I could do something on the fly today that'd just give you a quick overview, do you know? And that was the idea of it.
Is it possible to show the report of the 3D? Is that something possible? And the other one is the groups transfer from SketchUp, correct? I think that was a yes.
Yeah, groups.
Grouped, yeah.
Yeah, so everything is a separate group.
And yeah, if it's possible to show the report for the 3D would be great, would be amazing.
Yeah, hold on. Now I have to do a bit of jiggery pokery here. Hold on.
That's the technical term, right?
Yeah. Terrain. One. Oh, come on. Why are you not working? Ah, there we go. And we might as well focus in on this little spot here or something. I've set up standard reports for 3 different terrains. You can have any amount of them. And you can have any kind of report. Like the report is XML based with a little XML kind of programmer thing, and it's reasonably easy to follow. But I've got standard templates to get you started and get you running, basically. So there's the 3D, and it will park a chai up there if you just double click it. Here's that editor I was talking about. What you can do is click on the text and just put your chai beside it if it's not there. And like you can edit sizes, transparency. You can do, there's very little limit to it. If I just show you the other views, there's the other one. And there's the one zoomed in, if you ever need it. FRSI. Okay, it's picked a certain terrain. I can change that. Hold on. Where is it again?
Bob, just in the meantime here, Marcel asked, what version of mode do you recommend? Subscription or direct download?
Oh, I haven't seen much change in the time that I've had it. Now, I've only had it 6 months, or maybe a bit more than 6 months. But I haven't seen much change in the program, but just my own personal preference is to nearly go subscription, just because, you know, if things go wrong, you have support. If you know, oh, this is the big one actually. If your thermal bridge is a different update version to someone else's, sometimes it won't open someone else's files. So if you're planning on sharing between your office or between other offices, your actual mold files and not just the reports, then definitely go subscription. Otherwise, yeah, perpetual is fine. Plus, it's like, you know, when I first started in Passive House, God, 15 or so years ago, you know, nobody would buy solar panels in Ireland. And the people that did buy them funded the development of making them better. And now look at them, do you know? So I don't mind paying into something to support further development of what's already a great thing. You know?
And another question here, Bob. Have you done window frames in this version too?
Oh, I have, yeah, defo. The examples, the examples that you've seen in the presentation slides are all done in this program. And it's so handy. Actually, oh, if we had time, I would. I'd do a window fit in detail, or even an open one. Let me see. Oh yeah, here we go. No, sorry. Bear with me now 1 sec. I'll see if I can pull up a window fit in detail. So what's cool about this is, for all the divided air spaces, all the divided air cavities within a frame, you just paint on divided air cavity and it does it for you. And there's no jiggery pokery of, like, you know, setting it up or anything like that. You literally just paint them in. Watch, I'll just take out, you can take out materials as well, you can erase them like that. And to put in the frame cavities, you literally just set it to, oops, frame cavity, D4 unventilated, and it's horizontal. And then, oops. And that's it. That's your frame cavities done. Yes.
That's nice.
Really cool. The easiest one I've ever seen.
It's pretty awesome in big time.
How are we doing for time? We're 22.
We have a little bit of time, but we can also, as everybody, I'm sure, like me, is tired of Zoom. So if there isn't, I mean, like, these are great examples, and a pretty good kind of, I mean, our idea with this technical group was a teaser to the course, in that space. And I think it's the course, so everyone knows, is in a new program for Passive Canada. So it's a self-paced learning program. So they're pre-recorded videos with some chat and some other functions in it. So it's a bit of a trial space, if you will, that we're trying to test out. And those links to be able to take that course should go live in October, and go from there. I think maybe now that you've given us an overview, Robert, Marcel brought up a good point of, I think we all have a taste of what it can be within that course. What exactly is covered, or what?
Just so
one of the areas that Louise posted it, and I can do it again, or maybe Louise will, is there was the course
flyer, yeah,
that has a pretty good breakdown of what the modules in the course are. So that was way up earlier. We can fire that in again. And then also with the course, there was a discount for mold negotiated. So Passo's members that take the course do receive a discount from the mold software producer Dartwin.
Yeah. Oh, just on the version of Mold Simulator as well, there is a more advanced one that does dynamic glazier method moisture calculation. For our course, it's not needed. And honestly, if you're going to that level, you should really look at high growth thermal anyway. So you don't need the full dynamic temperature over time and glazier over time, like, you know. I just see, yeah. Sydney just had a question there. If you're working on a 3D model, can you cut a section to see what's inside? You can indeed. One thing you can do, I use a lot, is hide, just to move it out of the way. But the other thing as well is, oh, you mean in mold. Oh. I tell you what there is. I'll show you now. If I can find it. So if you have items inside, there's this outliner in materials, this one here, and then it has all the different parts, and you can basically click on the part and then go hide show selected, wireframe selected, unhide all. I haven't done a very good demonstration of that, but it is quite a good tool. Hold on. Sometimes it takes quite a minute to get itself together as well. Hold on. So you can see it on a mesh level, and then there is another way. You can leave it in solid mode and then just turn certain items off. Hide or show selected. Okay, it used to do that, but I think they've updated something, and I'll just send them an email and say they need to revert back to what it was, because it's a bit confusing at the moment. But yes, there's an outliner so that you can turn off the parts that are in external so that you can see the parts that are internal. Oh, yes, in mold. I don't know if you can cut a section in it. I actually don't, but I will look into that.
Just to let you guys know, I printed here the courses structure. I just got my Word document, put it in the PDF, so you know what's going to be covered in the sections. Okay, so it was a file that I just had to do like quickly, so don't mind any gaps or mistakes there, just to let you guys know what is going to be in it. But we'll send you the proper information as well. But I didn't want to leave you without an answer on what is the course structure.
Okay.
Yeah. I'm just checking if you have any further questions. You're welcome, Marcel. I don't see any further questions. Chris?
No, I got a couple problems. Like, just so everybody knows, I did record this. We will be posting it most likely in 2 places as fast as we can. One will be on YouTube, just for general viewing. That's typically what we do with the technical groups, to spread the word of Passos Canada. And then if AIBC, BC Housing, or PHI credits are required, we need to verify that you've watched it. So it'll probably be, at this point, go through multi-view. I just need to set that up, and that will be my afternoon project. And so there'll be 2 links coming out. So if most of you, there's a few people that came in late, where you can watch that. if the CPD credits are important, just make sure that you go through the multi-view link. I also know there's a number of, I did see the registration, so I know there's a number of bigger firms on this call. So if there was anyone in your office, there's a couple ways to show that off. So that is the plan. And I know that it's tough in these virtual things to get the enthusiasm. I appreciate Bob for giving us enthusiasm, and for what it's worth, you did hold everyone's attention the whole time, because often we have a bit of an attrition rate. And so I think the excitement was shown because everybody stuck around. So that was good.
That was a great job, Bob. It's just I want to thank you very much for the presentation. We got lots of thank you here from the audience. So it was really amazing. I guess you turned up this let's say kind of a boring section into a very nice section, though, right?
I don't know why I'm enthusiastic.
It was really fun, though. It's like it's about some only people who actually does those kind of calculations be like, oh, that's interesting. But no, it's pretty amazing. Congratulations on that.
Yeah, it's good stuff.
All right, with that note, we'll sign out a little earlier. So thanks again for everybody showing up. Thanks, Bob, for doing this for us. And I look forward to seeing everyone at the next event.
Okay.
Cheers. Thanks, guys.
Cheers, guys.
Cheers, bye. Bob, have a good evening, man. I know it's late for you. We'll chat soon.
Sound. Talk to you.
Bye.
Bye. Bye.